Let us now begin with our perceived unimodality of the distribution. It seems inescapably obvious when one looks at the graph that the atomic mass probabilities increase and then decrease. How could one verify such a phenomenon in general for an arbitrary value for the number of trials n and for an arbitrary value for the bias probability p? Well, naturally enough, if there is such a tendency, one might be tempted to consider what happens to subsequent values of the atomic mass function. And in particular, let us consider the ratio of the probability that there are exactly k successes to the probability that there are k minus 1 successes. We won't at this stage put any particular restrictions on what k may be, and so we just look at two consecutive values for the number of successes. For each of them, we have a binomial probability. For the probability in the numerator, we just have the ordinary binomial probability that appears on the top right of your screen, and that is the binomial coefficient times p to the k times q to the n minus k. In the denominator, we are looking at a success probability for exactly k minus 1 successes, and so all we have to do is take our expression for Bn of k and replace k throughout by k minus 1. And now we've got a fraction, and it's already beginning to look a little intimidating. But no matter, let us begin by expanding out the binomial coefficients. Remember that n choose k is n to the power k falling divided by k factorial, and n choose k minus 1 is n to the k minus 1 falling divided by k minus 1 factorial. And so if you write it out in gory detail, oh my goodness, we get a really messy, long expression, don't we? But things are going to simplify very quickly. The binomial coefficient n choose k in the numerator, and the binomial coefficient n choose k minus 1 in the denominator. Now, for the fraction on the left, you find that it has an extra factor n minus k plus 1 in the numerator and an extra factor k in the denominator. The powers of p and the powers of q likewise cancel the numerator and denominator, leaving an extra p in the numerator and an extra q in the denominator. Oh, now everything compacts and simplifies in a hurry, and we get a nice and compact little fraction. So the ratio of two successive binomial probabilities is given by n minus k plus 1 times p divided by k times q. What can we conclude from this? Bear in mind that we are looking for evidence of unimodality. That is, that the binomial probabilities are increasing up to a certain point and decreasing thereafter. If one is in the increasing portion of the curve, then the successive probabilities must be increasing, and therefore the ratio of successive probabilities must be bigger than 1. What now if bk is bigger than b of k minus 1? That says the fraction on the right is bigger than 1, and now we immediately have a criterion. A successive binomial probability is strictly larger if and only if n minus k plus 1 times p is larger than k times q. Let us savor this. This is an elegant and simple inequality, but of course we do want to simplify it a little bit further. Take the quantity minus k times p on the left of the inequality to the right-hand side. And now our inequality is transformed into saying n times p plus p exceeds k times p plus k times q. We feel irresistibly compelled to factor out k on the right, leaving you k times p plus q. But bear in mind that P is the success probability and Q is 1 minus P, the failure probability. Or in other words, P plus Q is equal to 1. We now have a beautiful and simple criterion. The successive binomial probability is larger provided NP plus P is larger than K. Or, in other words, we have a key conclusion. The binomial probabilities B of K increase as long as K is no larger than NP plus P and decrease thereafter. NP plus P, of course, in general is some real number. P, of course, is something between 0 and 1. So this says that around an integer next to n times P is where the maximum of the distribution occurs. Now, this already gives us some added evidence in favor of our estimation of a subpopulation parameter P from a sample. The binomial distribution has its maximum value at around n times P. Or in other words, Sn divided by n, the fraction of successes in a sample of size n, achieves its maximum value just around P.